Hello everyone, welcome to another video about the Infinite series. In this video we're going to talk about our last subtopic, which is Taylor and Maclaurin series. So this is the end video. This is the end of our module 3. So Taylor and Maclaurin series will be our last topic before ending the module 3 with unit tests. So, what is exactly Taylor and Maclaurin series? Why actually do we need to learn about Taylor and Maclaurin series? Have you ever wondered what happened inside the calculator, our calculator, when we type, for example, sinus 10 degree, for example? What is actually happening inside? It's quite impossible for a calculator to generate a right triangle of a 10 degree and derive a ratio between the opposite side with the hypotenuse and then get with the result of sinus 10 degree. So what happens inside our calculator is actually the approximation of the value of sinus 10 degree by simply using the operations that the calculator understands, which is arithmetic. So what happens inside our calculator is actually just the operation of addition, subtraction, division, powers, exponents, and so on. So actually, this is when Taylor and Maclaurin series becomes very useful. So Taylor and Maclaurin series is very useful to approximate a certain value, a value of function. We say approximate here because we actually do not have the exact value, but we try to approximate the exact value as close as possible using infinite series. So we're going to learn more about that in this topic. So what is actually a Taylor series? If a function f has derivative of all orders at x equals c, so if we have a function and it has derivative of all orders, so you can find like the first derivative, the second derivative, and so on. All order means like first derivative, second derivative, and so on. Then the Taylor series for fx at c is defined by this. So it's actually the infinite series of fn. This is like the end order derivative. So if the n is 2, it means the second derivative, and if it is 3, then the third derivative of the function f. And f and c means we plug in the value of c through the derivative of the f and divide by n factorial times x minus c to the power of n. If we expand this series, we will get fc, which is our function plugged in by the center, the c. So we say that c here is the center, as it's the same center with what we talk about in power series. So fc plus f dash c, which is the first derivative, and we plug in our center to the first derivative times x minus c plus the second derivative over 2 factorial x minus c and so on. So we have, this is our original function, and this is the, oh sorry, so this is the first derivative, and this is our second derivative, and so on and so forth. So we did the approximation by adding all the values of the function of the derivatives in all orders. So the orders will like will continue until infinity. However, it is quite impossible to calculate all this addition, all this summation, right, until infinity. The infinity, it's quite impossible to do it. So that's why usually we approximate the value of the function using nth Taylor polynomial. It means, so we actually make the Taylor series, but we want to stop at some n. So we usually call it nth Taylor polynomial of f at c. So p n x means is n Taylor polynomial of it at c. So we stop expanding the series. We stop expanding the series at n. So if we have, let's say we have p5x, means we expand this until x minus c to the power of 5, something like that. Yeah, so that's Taylor series. What is Maclaurin series? When c is 0, so here you see that our center is c. When the center is 0, so if we plug in C0, then you will get Maclaurin series. So Maclaurin series is actually Taylor series with C equals 0. So if we expand this, we actually get a pretty simpler function, summation of function, plus f x and plus f second derivative 0 x squared and so on. So this is our function, our Taylor and Maclaurin series. Okay, now let's try to expand a function using a Taylor series. Let's say I have function fx equal e to the power of x. So we're going to expand this using Taylor series with the center is at x equal 1. So we know that our c is 1. So we're going to expand it. So fx is e to the power of x. So if we want to find f1, it's actually e to the power of 1, which is e. We need the first derivative, so we have to find the derivative of fx, because e to the x is, the derivative is e to the x, so it's still there. We have f dash 1 is the same, and for the second derivative we have the same function, and for that we also have same function again. So actually the expansion, so our ex is actually f1 plus f dash 1 over 1 factorial, which is actually just f dash 1. Let me write f dash 1 with x minus c, the c is 1, plus f double dash 1 over 2 factorial with x minus 1 square plus f 1 over 3 factorial, oops, x minus 1 cube, and so on. So let's plug in. F1 is e, right? Plus f dash 1 is also e times x minus 1, plus we have f double dash is still e over 2 x minus 1 square, plus we actually have the same thing over here, e to the 3 factorial x minus 1 cube plus dash dash dash. So we always have e over here. So our series is actually sum of, we start with n equals 0 to infinity, e times, as you can see here, so let me put a note. Here we have to the power of 1, this is 1, 2, 3. You see that this is like the same with our n. So this is n is 0 over here. We have x minus 1, 0. It's minus 1, minus 2. So we have our x minus 1 times n over, we have here we have our factorial. Let me change color first. Okay, we have over here, this is actually 0 factorial, this is 1 factorial, we have 2 factorial, 3 factorial, it's actually n factorial. Okay, so this is our expansion of e to the x centered at x equal 1. So actually the expansion of Taylor series is different based on the center, but it actually doesn't really make any difference. We'll see why, and I'm going to show you whether the center really significantly change how the function going to be approached. Now using the same function, we're going to find the Maclaurin expansion. Because it's Maclaurin, then the center will be at x equals 0. So we actually did the same thing what we did before about the derivative over here. Here is actually the same, right? What makes it different is just we don't plug in f1, but we plug in f0 because our center is 0. So let's make our expansion. We have fx is e to the x, we have f0 will be e to the 0, which is 1. So f dash x will be e to the x again, and f prime 0 will be e0, which is 1. So any value will be the same like that. So we can approximate, our function will be f0 plus f prime 0 with x, because it should be x minus c, but our c is 0, right? So let me rewrite here 0 so that you understand that it's because it's minus 0, plus 2f double prime 0 over 2 x minus 0 square plus f dot over 3 factorial x minus 0 cube, and so on. So we have f0 is actually 1 plus 1 times x, which is just x, plus it's 1 over 2, it's half x squared plus, so we have here 1 over, let me only like don't evaluate the 3 factorial just to make it easier to find the general term, x cubed plus da da da. Then we have, so our series starting with 0. So we have over here the power, it's actually x0. This is 1, this is 2, this is 3. You can write x to the n over, let me change color. This is actually 1 factorial, 2 factorial, 3 factorial, and this is actually 0 factorial. You have n factorial here. Okay, it's the expansion. See that it's different. Our expansion is quite different, right? So the different expansion may lead to different value of e to the x. So based on the value of x, we might come up with different value of e to the x. It's like it will differ based on the expansion. I will show you when we should, so which is actually better, Taylor or Maclaurin expansion. So it's, if I paraphrase this question, is actually when we choose c equals 0, and when choosing c is not 0. So that's the question that we are going to simulate in the next video, the next slide. So here I have a GeoGebra simulation of the Taylor expansion of e to the x. So the one, as you can see here, our red curve is actually the approximation of e to the x using Taylor expansion with the center at 1, and the blue one is Taylor expansion using the center is 0, or it's actually the Maclaurin expansion. So let me hide that first. So this is the actual function of e to the x, the black one. So e to the x, the curve, the graph is like this, right? Like this. So when let me change the n. So what I want to show you is actually what happened. So we have our expansion, right? So when we expand, for example, we use the polynomial degree 4. It means we use the Taylor expansion, but we stop when the power is to the power of 4. We actually have our series over here. So let's try with the center one first. It's the red one. The red one is the curve showing the value of the series, the value of the Taylor series with when we expand the Taylor series with the center of 1. So as you can see, when, let me change the n, when n equals 0, our series is actually just e. So 2.72 is just e. So as you can see, this is the red line over here, and the function, it's really not approaching our e to the x. It's not approaching our black curve over here. When we add the degree, so we add another term, it gets quite close to our original function, right? So it gets close. When we add another term, for example, and fourth, so as you can see, this is our expansion or clearly over here. So e plus e times x minus 1 plus e, so 2.72 is e, right? E times x minus 1 square over 2 and so on until to the power of 5. We have our red curve, our Taylor series get very close to our original function. So this is what Taylor series did. If we get more degrees coming, the higher degree, polynomial degree, see that it gets really, really, really close to our original function of e to the x. Okay, let me put it back here. Now, what about the Maclaurin series? Well, the Maclaurin, the blue one. Our Maclaurin series did actually the same thing. When n 0, it's just a horizontal line. 1, it's going this way, 2, 7, and so on. It gets really, really close to e to the x. So practically, there's no significant difference between uh, Taylor or Maclaurin series when we expand the function of e to the x. But what makes it different? Why, if it's not different, why should we learn the both things? Why don't we just learn Taylor, or why don't we just learn Maclaurin only? So this is when it gets very interesting. Let's go back to n to 0. So remember the red one? The red one is our Taylor series, and the blue one is our Maclaurin series. It gets interesting when we have our first degree. When we try to approach x equal 1 over here, x equal 1, you will see that our red curve approaching it faster than our blue curve. Our blue here, actually blue line, yeah, the red line. So the red series is actually approaching the value of e to the x with x equal 1 faster than the blue series, which is the Maclaurin. Division 2 and 2, oops, here. Okay, we have n2. As you can see, our red curve is closer to the a. Here I have 0.8. It's actually the value of e to the 1 is closer than our blue line. So the Taylor, which is centered at 1, is closer than the Maclaurin, which is centered at 0. So this is what makes Taylor and Maclaurin different. When we try to approach a value of e to the 1, so the x here is 1, the center should be closer to the value of x that we're going to approach, because we are trying to approach e to the 1 with x equal 1. Then the center of our series is more efficient if we choose the center as 1, because 1 is closer to 1 of power here. 0, yes, it will eventually approximate the function, but because 0 to 1 is quite far compared to 1 to 1, that's why Taylor series is more efficient to approach the value. What if we want to approach e to the 0, x to the 0, then the Maclaurin will be more efficient. That's why, as you can see here, when we this is the when we have here 0, our blue curve is approaching more effectively than our red curve. See, that's why. So When choosing Maclaurin, when you try to approach a value of x close to 0, when using Taylor, then for example you approach a value not 0. For example, I want to approach e to the power of 2, then you have to use a Taylor, so that you will have a Taylor with center at c equal true. Now, now let's try to approximate the value of sinus 0.1 using 6-degree Taylor polynomial. So continuing what we have learned, we are trying to approach, this is our value of x, 0.1. It's very close to 0, right? So let's took our center is 0. So we actually did Maclaurin polynomial, because we are asked to use 6 degrees, so we don't have to expand it until like infinity. We're going to expand only when the uh, power gets to 6. Okay, let's do it. So we have our, because we tried to approximate the value of sinus, so our function is actually sinus x. Okay, and we have, so f, because our center here is 0, the f0, which actually sinus 0 is 0. Now the first derivative of sinus is cos x. F prime 0, which is cos 0, is actually 1. Now let's continue. So because it's 6th degree, we have to find the derivative until 6th order. Okay, second cos is actually minus sinus x f, so we have f double prime 0 is minus sinus 0, which is just 0. Continue, derivative of this is actually minus sinus, so minus cos x f blah, 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 0 is minus 1. F fourth, cos is minus sine, minus minus sinus x, so we already get back to the first, so we actually going back there, right? So let's just write f5, the fifth derivative will be the same with that. We have f5 is 1 and f6x is actually same with that, is minus sinus x, so f6 0 is 0. Okay, so our expansion, because it's 6 only, so we can find like sinus x approximate. So because we don't know exactly, we're going to use this approximation sign. So we have the first one is sinus 0 is f0 plus f prime 0 with x plus f double prime 0 x squared over 2 plus f triple prime, can I say it? I don't know. Okay, and so on. So we have the value over here. F0 is actually until 6, yeah? I cannot write this. I have to say F6. Oh, let me erase. Okay, let me erase this. I have to make it specific. So I have a f6 x to the power of 6 over 6 factorial. So we have our value. See that here when the derivative, the first derivative is 0, the second derivative is 0, sorry, the original function read to 0, second derivative 0, fourth derivative 0, sixth derivative 0. So actually we have to consider only when the power of x, or the derivative, is the odd order. So the first, the third, and the fifth derivative. So we actually did 0 plus the first derivative is like, it's 1 times x is just x, and it's another 0. We have the third one will be minus, so we have y minus, for because it's the third one, we have 3 factorial through x cube, and the plus is 0, and the fifth one, it's 1 again, so we have plus 1 over 5 factorial x to the power of 5 plus 0. So we have, it's actually x minus 1, 3 factorial is 6, x cube plus 1 over 120 x to the power of 5. So when we want to find sinus 0.1, we actually just plug in 0.1 to x. So we have 0.1 minus 6, 0.1 cube plus 1 over 120 of 0.1 to the power of 5. So we have 0.1 minus, it's actually like 0.001 over 6 plus 0.1234 over 120. So it will be like something about 0.0017, something like that. You can do the calculation using the calculator to find this. So this is pretty much the approximation when you get the, so this is actually what's happening inside your calculator. It's only like calculating the summation and subtraction and power, that makes it like easier to understood by calculator. And besides, it's very like interesting how a sinus trigonometric function is being approached by just a simple series. Okay, so this is the end of unit 3 module, which is infinite series. So we're going to have unit test 3. I'm going to inform you later the detail about it. So see you everyone, and have a nice day.